So I'm Justin. I work at OMSI. I design technology for exhibits, but I started out in the music business and went to audio engineering school and learned a lot about signal flow and synthesis, and I've been playing since I was 13 or 14. A lot of the simpler kind, the kind with keys and a few buttons on them. And let's see. So I just want to start off with getting VCV Rack. If you don't already have it installed, just go to vcvrack.com. It's free. You do have to sign up. I'm already logged in, but all you have to do is...
Yeah, I just did the free one. They didn't ask for anything.
Yeah. Oh, okay. Yeah. So when you register and log in, basically what they've done is abstract away the having to download different plugins. Because the awesome thing about VCV Rack is it has a good suite of plugins built into it, but there's also dozens and dozens and dozens, maybe 100 at this point, of vendors who design their own free plugins. So any type of module you can think of, different types of filters, oscillators. So once you're logged in, and you'll log into, skip that. You'll log in here to get access to your library. We're going to use the built-in ones today, but it's just good to know altogether. You go to library and you'll see there's just all sorts of different, dozens of brands. We'll just pick, what's it called? Audible Instruments. For example, these are clones of an open source hardware brand of modules called Mutable. And you can just see all of these different gate here, there's an oscillator. So basically by brand, you'll see when you find something you like, you can just hit add and it will add it to your library and it'll just automatically download. So then you'll see shebang. Takes a minute, but. So that's how you can manage libraries, and there's a couple brands that I can recommend, like right off the bat, like Audible. There's JW Modules has a really good simple clock. Or no, yeah, there's a clock and a quantizer, which we'll go into. Volt makes really good filters. So there's a few different brands to check out. So if you're going through installing or setting up, we can just start in on audio synthesis. So synths come in many forms. You see, like, this is the Yamaha Dx7. It's a famous FM synth. Not as fun to program. You see, I mean, it's easy to play. You got your keys right in front of you. It's easy to pick presets. Programming it, making custom sounds is kind of hard because you're picking a button and hitting plus or minus. Not very friendly to program. But good at recalling presets. You want a piano sound, you hit one button. You want a horn sound. It's not a very good horn sound, but you hit it. So down here would be the Korg MS-20. Very cool analog synth, semi-modular actually. Everything is structured in a certain way. Like it goes from oscillator to filter to amplifier, but you can break the signal path and add in your own. You can run this to a different modular synth, or you can decide that you want the amplifier before the filter. So basically it gives you enough of a preset signal path that you can hit a key and get a sound, but there's no presets. Everything is set to where the knobs are. So that's like a level of playability, but just knob per function functionality. And then you can get to absurd levels of, I have plenty of money and I can buy this much Euro rack. which, you know, each of these modules, I don't know, it's between 150 and $700 or $800. So this is Richard Devine's setup. He gets paid to review and promote modules, so I don't know how much of that he's bought or was sent to him so he could post it on his Instagram. So, but yeah, that's a level and requires a lot of power management and everything. So the fun thing about VCV Rack is you can do something as absurd as this much custom signal path for free, which is much more in my price range than this sort of setup. So I just want to talk about the nature of sound a little bit. Sound is always vibration. Sound is like air vibrating, and it's air pressure waves. So when you see a speaker pushing out, especially like a subwoofer, you see a speaker kind of expanding and contracting, that's pushing air. And if you think about a guitar string or even a spring or what is that, a door stopper, it's basically going back and forth. And that oscillation of air moving is what creates sound to us. And the speed at which it does that is frequency. So if you know, this is lower frequency, this is higher frequency. And that would be the period in the waveform. So if you have a low frequency range, we'll say like 60 hertz. Hertz is the number of times that this wave period happens per second. So 60 hertz would be like a lower, higher, somewhere in here. So that would be 60 vibrations of that cycle per second. And then something higher, say like, that's like 440 vibrations per second. So the human ear can hear about 20 hertz to 20,000 hertz if you're young. I think mine's down to about 16 or 17K now. Your high frequency perception rolls off as you get older, which is unfortunate, but it's mostly very tinny sounds up there. So when you're looking at analog sound, or you're looking at something like a string, like a guitar string being plucked and vibrating, that's just pushing out waves. So when you're picking up sound, it's kind of a sidetrack, but things that convert voltage to sound are called transducers or sound to voltage. So a microphone is a transducer because there's a diaphragm in a microphone that when sound pressure waves, air vibrating, moves it, it converts that into voltage. And on the other side, a speaker is also a transducer because it takes the voltage, which is alternating, you know, the voltage moves in those same sound waves, converts that back into air pushing. You can actually take a speaker and use it as a microphone. It's not very good at it, but if you put it in front of a kick drum, you can actually get that kind of, you can get the hit out of it. It's kind of interesting. Technically, you could use a microphone as a speaker too, but you're going to blow it up immediately. So don't try that one. It's pretty funny, but. So, when you open VCV Rack, you pretty much be presented with a preset patch. The one thing we're going to want to keep out of this, just going to, so to give you an idea, here's some of the basic stuff of VCV Rack.
Is that the audio module?
Yeah, the audio module. So,
I didn't know what a module is, to be honest.
yeah, okay, so this is the paradigm known as modular synthesis. And back to, you know, this sort of thing. Basically, what modular synthesis is each module has a function, sometimes more than one, but the idea is that you can patch whatever function you want to anywhere you want because it's all voltages. So audio is voltage in this, And the other half of this is control voltage, which is using voltage to control basically the movement of knobs or how it interacts with another module. So there's a couple different signal paths. So what I'm going to do, and there's a few, so the idea of VCV rack here, we get a couple interface things. You can grab part of a module that's not a control, like not the knobs, but you can grab a module here, and we can move them around the rack. If you hold control and scroll, well, it'll be command on Macs. You can zoom in and out, so I'm going to keep it to like 2 rows here for now. You can use the arrows to scroll around the rack, but we'll just try to keep it in one screen for now. So the audio module is basically your output, and that's the sound card on your computer. So I think there's only a couple of us in here, so it'll be all right. But when you're using headphones especially, just start out with the volume low and your system volume low too. Sometimes it can surprise you, and it's just better to have that be low than to damage your ears making silly experimental music. So with the audio, I think you're all on Macs, so that'll be easy. Click up here and it'll give you your audio driver, which on your Macs will be Core Audio. If you're using Windows, you want to hit Wasapi, and then your device. I'm on the, oh, I just killed my device, didn't I? Let's see. I'm going to use the Intel Display Audio because I'm running this projector here. But you'll want to pick whatever your sound card is that your headphones are on. So it'll just be like Realtek Audio, or with the Macs, it pretty much is just automatic unless you have an external interface. But with the built-in audio, it's all good. If you're using Bluetooth, you'll pick the Bluetooth interface. And then everything else you can leave like that. So I'm going to just highlight. If you drag any empty area of your rack, you can just highlight, hit delete. And if you mess something up, like if you actually accidentally delete the audio too or anything like that, you can Control Z and undo, just like anything else. I mean, there's a lot of common shortcuts. I can Control C and Control V and duplicate it. But I'm just going to go ahead and delete everything. And if you right click on an empty area of the rack, it gives you, this is what I have too many brands installed. So if you click brand, if you have any of the other ones installed, you'll see everything all together, but you can click brand and go down to VCV, and these will be the built-in ones that we're using today. So I'm going to add a scope, first of all, and I can just drag this over here. And the scope shows you kind of these waveforms in a way that you can, so that you can see it and understand what's happening visually. When you're making music, you want to do it by ear a lot, but sometimes it just kind of helps to see what's happening, especially with some of these control voltage signals. We can drag anything into the input here and see how it works. So I'm not going to plug in the output yet, so it'll just get loud pretty quickly. But I'm going to right click, and I'm going to click VCO, and that's a voltage controlled oscillator. So all the voltage in here is of course simulated unless you count the actual voltage going through the computer, but whatever. So oscillators are voltage oscillating, same thing as air vibrating, right? So this is going to be what creates our initial tone. So I'm going to take there you see sin, tri, sol, and square. So that's a sine wave. Might look familiar, just a very smooth wave. Triangle wave, sol wave, and square wave are all kind of indicative of what, of what they look like on the scope. So if you just left click on the output port, you can just drag a cable over here to in. And I'm going to turn the time down so we can see what's happening, or turn it up rather. Since the time range kind of pops up in a little info box as you're hovering over these controls. And I'm going to click trigger too, this works just like an oscilloscope in electronics. So when it sees, you can use the trigger to keep it kind of locked in so we can see what's happening. So this is a sine wave. It's very basic wave. I'm just going to plug it in for a second. You can hear what it sounds like. Very smooth wave. So this is the frequency we can control. Again, just like seeing here, low frequency. And as I hover over it, you can actually see the frequency. It says 104 hertz. So now I can go back and say, I can just type in the field here, say 60 hertz. You can barely hear that. That's like an 808 kick drum frequency. So if you want to say like middle A, I'm going to turn this down first. Say 440 hertz. So that's the A below middle C on a piano. This isn't going to be heavy on music theory at all. We're just going to kind of go with sound design. So don't worry if you don't get the kind of theory, but on a keyboard it would be somewhere near the middle, basically. So I can click on this cable and just drag it into like blank territory and it will remove it. So there's our sine wave. If I click this and drag it over to the next output port, and as you can see, it's not universal because if you look at all these different brands of modules, everybody has their own design, and some of them are good, some of them are obviously not graphic designers. Not being judgmental because, well, there you go. So these don't all follow the same convention. I can just hit escape to get out of there. But at least with the VCV modules, you can tell inputs by the silver background around them. There's no background. All the outputs on their modules have black around them. But when you hover on them, you can see pulse width modulation input, sawtooth output. So you can always tell whether a module or whether a jack is an input or an output. So similarly, here's a triangle wave. And this oscillator is actually modeled after an analog one. You can have super clean, as you would imagine, just drawing a triangle. But this one actually has a little bit of flavor of like old analog synths where it's just analog circuitry. It's not doing it perfectly. Pull the volume back down. Saw wave. And square wave, which isn't even very square on here because, again, this is emulating an analog circuit where you would see you're telling the voltage to go up and down. So you can see that the transition's pretty fast, but if you could imagine just a crappy old analog circuit with not very good capacitors, say from the 70s, it's kind of overshooting. It's kind of like overshooting. Say it wants to go up to 1 volt, it'll overshoot a little bit, and then over time it'll just kind of die off. So that's what's happening. You can find other oscillators out there that have perfect shapes, but you know, it's all character. So that's a square wave. A fun thing we can do with this is that we've just been using frequency control so far. Below it is pulse width. Now if I do anything with pulse width here on saw or sine or triangle, it won't do anything. What you'll see with square wave is you'll notice that, and this is the 0 point here because audio goes back and forth. Think of this 0 volts line as being like a speaker at rest, and look at positive voltage as the speaker pushing out, and the negative voltage below 0 is the speaker pulling back in. So as it's vibrating, it's doing that. This would be the speaker at rest in the middle. But when you're looking at the square wave, you look at the width of this cycle of negative voltage and the width of this cycle of positive voltage, they're about equal, so it's 50-50. And you'll see that kind of on here, we're at 50%. Another thing you can do, sorry, just running back through the interface, you can double click any of these controls to bring them back to their default. Or you can right click and click initialize. But yeah, so the pulse width being 50% or even, pull it down, it thins out the amount of upward cycle. So, you'll notice so far, of course, too, that I'm kind of just raising the volume and lowering the volume because there's nothing to control it except for the volume itself. Cool. And so far I've also been just using the pitch manually, changing the frequency manually. I'm going to scroll out a little bit here. And I'm going to right click and just select VCV again. And I'm going to pick the basic MIDI to CV. So that CV is control voltage, right? Since we don't have anything to send an analog voltage into this right now, I can use MIDI to CV, and MIDI is musical instrument digital interface. So if you're familiar with any like keyboard-based thing like this, or like, you know, when you see a keyboard or just a box with a bunch of knobs, it's usually a MIDI controller. And what that does is it sends out commands. It's kind of a language. It doesn't send out sounds. It just sends out like, you know, I'm hitting the C3 note at this velocity, and now I've let go of it. So we can approximate without a MIDI controller. I'll say, just click on the Windows MIDI part here, say computer keyboard and mouse, and then that'll let us use the keyboard as a basic MIDI controller. So I'm going to keep the volume kind of low. We'll just give it a saw wave. And this is our basic signal flow. We're running from the oscillator into the scope so I can see it, and out from the scope into the audio output. So the first little bit of control voltage I'm going to do is this V oct. So basically controlling pitch in Eurorack or in VCV rack. There's a standard called volts per octave. So that means that like if you're at 1 volt, you're at you know, your first octave. 2 volts, you're at the second octave. And then everything's kind of relative to there. So you'll see if I initialize this, you'll see it says 261.63 hertz, and that seems like a weird middle point, but what that is middle C. So it kind of keeps you in tune. And you know, if you're just writing stuff within Eurorack, or if you're just writing stuff for yourself, and it doesn't really matter if you're in key or not, but if you're playing with other musicians, and you're not doing experimental scales, then it helps to kind of have a standard of what notes you're playing, you know. Guitars have frets usually, pianos have keys. This kind of keeps you locked into that. So what I'm going to do is take our volts per octave, so that's going to be controlling pitch, and you can see it just matches up. There's that output that'll come from hitting the keys on the keyboard, and the input of our oscillator. So I'm just going to drag that over there. And now if you hit keys on the keyboard, and that key map is actually here, we'll show you. You can actually change the octaves so that you're like tilde in one key, and then it kind of acts like a piano keyboard here, and then this is up to the next octave. So. And again, we're still only controlling the pitch. We haven't figured out a way yet to handle the note on and note off, right? And we don't just want it making noise all the time. So I'm just going to go ahead and drag this off. And so here's where we'll start thinking about signal flow. The rule of thumb to keep in mind is always go from out to in, and that'll kind of help you keep track of what's happening. So I'm going to right click, and we've still got our VCV modules up here. I'm going to click VCA, which is voltage controlled amplifier, and an amplifier is basically your volume, right? So if I go from out to in, we'll say saw wave to the input of the VCA, and we'll take the output of the VCA, go into our scope, which is plugged into our audio, Looks the same, right? But now I have a volume knob here, or fader. And what you'll see hooked to it, you'll see there's this input jack here. And that's CV input, right? So that basically lets you control the volume without having to resort to doing it manually, because that would be a lot. So what should we do to control the volume here? And you'll see when there's nothing plugged into this, this is just blank. It's just manually controlled. But when we plug it in, it'll take over control from that volume that's built in. So I'm going to take the gate, and what the gate is, I can actually show you on the scope. I'll make another scope, it'll be easier. So I'm going to take the gate out, put it into the input here, and turn it up a little bit. So you see every time I press the key, and I'm just pressing keys so you can hear the pitch change. But every time I press it, you get this square wave. And that's basically, if I hold down a key, you'll see it just goes high. And as soon as I let go, hit the key, let go, that it's basically gating. This is open, you know, this is the key press, this is not pressed. So I'll just get rid of the scope. I could just click on the module, hit delete. And I'm just gonna go to a lower pitch because that's annoying. So we're gonna take the gate from our Midi to CV, and we're just gonna drop it into the VCA. And now you'll see that it's muted. But when I hit a key, really simple. I mean, it's just straight on and off. It's kind of like playing an old organ where there's not any real control. There's not like, if you pluck a guitar string, it has what's called a decay. You know, it starts out strong and it just gets quieter as that vibration kind of comes to rest. So we don't really have that here. We just have on, off. But that's enough to start. Now what we might want to do to give that a little more, make a little more sense out of it, is to right click, and I'm just going to add, this is ADSR. What this is it's called an envelope. The ADSR stands for attack, decay, sustain, release, which are the 4 stages of the envelope you can see right here. So shrink this down a little bit. And you'll see we have a gate input right here. So I'm just going to go ahead and take the control voltage from the, I'm just going to mute that. Control voltage from the gate from our Midi to CV, and just drop that in the gate. And you'll see as I hit a key, it goes through these phases. It'll actually tell you which phase it's on, which is nice for being able to tell how long each of these phases takes. So we still have our VCA here. This gives us a little more control over how fast the note hits full volume, and then it decays, and then as you're holding on to the note, how long it sustains, or at what level it sustains. And then the release is once you let go of the key, does it stop instantly, or does it just kind of ride out? So I'm going to take our envelope output here and run that into the VCA. Bring our volume back up. You see if I do a slow attack, it rises over time. And then once it hits that peak, so I'll pull that down. You see that's how fast or slow it hits that downslope. And then sustain is the volume level of that downslope. So if we just turn decay and sustain all the way up, it'll just stay at that maximum as long as you hold the key down. So we'll just try to take this to somewhere reasonable in the middle. And I'll pull the release all the way down. You'll hear that as soon as I let go of the key, it's just instant. And if I extend the release, letting go of the key, And you can actually see on the little tooltip there, it says 1037 milliseconds. So that's like a second after I let go of it before the volume dissipates. Cool. So we can do something plucky like. So that gives us a little more control over the character of the of the notes playing. And the next thing we might want to do is we'll say we want to kind of control the timbre, the tonal quality of this oscillator, because as it is, it's just this kind of sharp sound. So I'm going to right click and we'll add a VCF, which is a voltage controlled filter. And you can see, again, the tooltips are really helpful for this. You can hover over and kind of get a reminder of what these things are. Because I know it's a lot of letters to start out as VCO, VCF. But really with the built-in modules, they should have just labeled it like oscillator, filter, low frequency oscillator, you know. But I'm gonna go ahead and add a VCF, this filter. And what the filter does is it filters out frequency ranges. So I'm gonna take that sawtooth out from our VCA and we'll run it into the VCF. So that gives us, we're now to there. And there's two different outputs here, LPF and HPF. That's low pass filter and high pass filter. So the low pass filter cuts out the highs. It lets the low frequencies pass and it cuts the high frequencies. High pass filter does the opposite, cuts out the lows, leaves you with the highs. So I'm going to start with a high pass, just for demonstration. Now the cutoff frequency is the point at which it cuts. So say like, I should have one of these in the demonstration, but there you go. So this gives you an idea. If you were looking at, not necessarily the scope in terms of waveform, but if you're looking at this as low frequency and high frequency, this is cutting your lows. And different filters have different qualities, so they'll slope off a little slower or a little more sharply, not sure. Looking for a good resonance. And the other thing that most musical, like synthesizer filters will have is called a resonance peak. And that's basically, if you're looking at, here's your low frequencies and we're cutting off the highs, but right before the highs, we're turning it up. It's like an equalizer, we're spiking the frequency right before the cutoff. And that adds like kind of it's a resonant character. So I can give you an idea of this. We'll just, since we're doing high pass right now, if I turn it all the way down, we're at the low frequency point. Cutoff frequency is 8 hertz, which you can't even hear. So you're getting the full sound. I'm just going to bring up the sustain so we can keep this going. But as I turn it up, it starts cutting out our lower harmonics. Now I'm going to move this over to low pass filter. And again, if you like drop your cable or whatever like that, you can actually go either way. You can go from in to out, but just for consistency and signal flow, I like to go from out to in. So this is too low for us to hear, really. So if you add the resonance, then you get this kind of peak. And this is, again, like modeled after an analog circuit, so it's not scientific, it's not like mathematically accurate as a perfect frequency cutoff. So you get this weird distortion as you turn up the resonance. But that's all character, so. If you turn it up all the way, it does this thing called self-oscillating. And I can actually just like get rid of the input even. And it's just creating a sine wave on its own. bring our sine wave back in, pull the resonance down a little bit. And it also has a drive, which is like overdrive on a guitar. These two kind of interact with each other in a weird way that's not really linear, but you can see it's giving us, these are called harmonics. You kind of got these, the wave is like folding back in on itself. So that gives us a lot of control over the characteristics. But again, right now I'm kind of just controlling all the knobs manually, right? And you can only play so many notes and twist so many knobs at a time. So what we want to do is start giving this control over itself, with kind of the goal of like giving it some automatic things to do. We can start sequencing things, we can make random things, generative patches that just kind of decide their own notes and their own qualities. So, let's say we want to just give this a little bit of back and forth. So I'm going to right click and click LFO, which is low frequency oscillator. These are essentially the same thing, but this is way down right here, 2 hertz. Is the center point of this one. And if it starts getting crowded around here, sorry, you can click on view, and there's cable opacity here. So you can kind of get these out of your way, and you can actually adjust the cable tension. Whatever works for you, but when you hover over one of the ports, it shows you where that's going, which is nice. Kind of kicks the opacity all the way up. So anyway, so I'm kind of keeping my control stuff down here, just for organization. This is my audio path up here. Doesn't matter what you do, but it really helps when you start building bigger patches to find some form of organization that works for you. So my low frequency oscillator, you see the same waveforms on this one. I'm just going to drag this into input 2 of the scope here. Actually, I'm just going to skip. I'm going to make another scope. That'll be easier. I'll drag our sine wave over here into the input. And you can see we've got this. If I turn the time up to like our audio rate here, this is doing the same thing. It's putting out voltage in the same range, but 2 hertz is outside that 20 to 20K range of human hearing. If I pull this all the way up, you'll see it goes up to like 1,000 hertz or so. And if we take that, you'll see it is an oscillator. But the point of a low frequency oscillator is it kind of gives us more control over control voltages, or it's more useful for control voltages. So you notice that we've got this range of smaller knobs here, and these inputs that we haven't used yet on these. So I'm going to take our sine wave, and I'm going to drop it into the cutoff input, so the frequency input. And you can actually see, this is easier to see, like you'll see there's kind of that color, that light in there, which when you're looking at audio range just kind of shows that it's on. But you can actually see here our sine wave coming in and out, which is a really nice thing that VCV Rack does, because you can kind of see what's happening. If I hit a note too, you'll see it on the on our VCA. Really nice to tell what's going on. But I'm hitting a note, and this isn't affecting it yet. I'll show you another thing you can do. If you hit Control on PC or Command on Mac, and then click your output port here, you can actually, this is called molting, so multiplying your signal out. Just going to put this, so I can put it on the scope as well, not have to run it through it. So you see we've got this low frequency oscillator going into the filter, but it's not affecting it yet. So what we have here is basically a bipolar knob that, you know, when you initialize it goes to center, and that means it's not actually going in to affect the cutoff in any way. But if we turn it to up, then it's affecting it in a positive way, and you'll see this is like, there's your 0 line where it's at rest, and this is basically only turning it up from this point. So if I pull it down, it's only going from here to how much I turn it. So if I turn this all the way up, it'll just kick from where I leave it to all the way to the top. And I can increase that range, decrease that range. So it's nice to have a little bit of room there. And the other thing is, once you turn it left of center, it does the reverse. So what's happening here is it's only turning down from that point. And you'll notice that because we're below the frequency of the note, we're not really hearing anything. But as we turn it up, now it's doing this. It's turning down. So I'm going to bring this down a little bit, bring the range up. Kind of got this. Cool. And if I hold a note down and then you can make this like glacially slow. So we can make something that's like slow and subtle, like here's our note, and we'll just give it a little bit of influence over it. Or we can just be drastic and do. And as we go into the audio range, it does something that's called, I mean, technically all of this is frequency modulation, but when you start affecting things that are in the audio range with other audio signals, we call it FM, frequency modulation. And that just kind of gives it some rich tonal quality. So you can see how quickly we can kind of get to a complex sound here. So I'll bring that back to something reasonable-ish. So that's kind of your first, well, between the ADSR, the envelope, which I can actually show you here too. We'll controller command click on the envelope and bring that into the scope. Sometimes these scopes get a little buggy. I'll make a new scope. There you go. So you can see with that fast attack, you can kind of see in real time what's happening, right? But you can use anything in this to control anything. Since they're all voltages, you can use sound signals to control voltage. You know, you can use sound signals to control the movement of knobs at a rate that's faster than you could humanly turn it. You can use control voltage to control things. It's all control voltage, basically. You just don't want to run this like 2 hertz signal. You don't want to run something that's slow in your audio path, because now you're pushing the speaker, you know, say you do 1 hertz, now you're pushing the speaker 1 time per second, and the longer that it has to hold out, is more power that the speaker's using. So if it has to push out and stay there, because speakers are just like magnetically actuated transducers, now you're forcing this electromagnet to like push the speaker out all the way for a longer time than it's supposed to. It wants to vibrate. It doesn't want to just push out and stay there and pull all the way back. So That's where you get speakers starting to smoke. And that's not what you want. So avoid running those super low voltages through your speakers. 20 hertz though, sounds awesome in the trunk of a car, you know. But just gotta limit the amount of that very low frequency. And you'll see that in scope. If you're looking at like your master output and you've got like say a whole track coming through here, but you have like 2 hertz mixed in with it, you'll see the whole thing just kind of phasing with it, so. But short of that, anything can control anything, regardless of its frequency here. So if I wanted to, let's see. We can take that LFO back out of here, and I can actually, I'll click ADSR and hit Control C, Control V. No, you have to click off of it first. Control V, we can paste. I can make this envelope control the filter cutoff now. So I will controller command click on the gate and mult this out to the second envelope. Now when I hit a note, you'll see we've got both of them firing. I'm just going to go ahead and now as that goes, it's turning the cutoff knob just as it would, you know, manipulate the VCA. Like this is basically turning the volume knob at whatever speed the envelope dictates, and this is just doing the same with the VCS. So that's fun for like. So now we've got this kind of snappy signal that we can control out of that. Well, the fun part is you're not limited to, you know, just having this, just having the envelope or just having the LFO. We can actually mix control voltage signals. So I'll just right click and I will add in, I'll just add in a mix. It's pretty self-explanatory. So I'm going to keep this. This one is for our VCA, so I'm going to move this over here just to kind of keep them together. These are, so when you're using control voltage to change the another function, we call that modulation. So like when you're using this LFO, we're modulating the resonance now, or the drive. So I'm going to take my mix, and I'm just going to take our envelope out into it, and then I'll take a triangle wave out of our LFO and also put that there. And you see down at the bottom we have this mix output, and you can see what's going on with both of these signals here as I hit a button. I'll up the release a little bit, there you go. And I'll pull this down a little bit so you can see what's happening. And I'm going to drop this into the scope. And so you can see we're getting this triangle wave. Slow it down a little bit. But when I hit a key, we're kind of getting out of the range, but the idea. It actually adds that envelope to the LFO that's already happening. And another thing with the LFO is you see we're only doing positive voltage right here, so it would only be turning the knob up unless we're using one of these to invert. So what we can click on here is this offset knob. And we're hovering over it. When it's lit up, it's unipolar, which means it's only going north of the equator here. If I click on it, it switches to bipolar, and now we're actually going up and down from the centered value that would be going into the knob. So now when I hit a note, we're getting the envelope, pull the decay down, getting the envelope mixed with our signal, or our LFO signal. So I'm going to drop that into the cutoff. So now we're getting the wobble of that, but also an extra peak as I hit the note initially. If I bring the attack up. So is that making sense so far? Ish. I mean, it's a lot of stuff to take in all at once. I'm kind of showing like the possibilities and hopefully building in the signal flow enough that that you can keep experimenting. Because that's the main thing with all this is like you won't absorb it all at once, but if you have enough to play with, then you'll get a more in-depth feeling as you go. And that's a great thing about having the scope. Is you can see what's happening with all the voltages. Using this time knob to kind of catch your range. If I take the LFO, you can see it draws as it goes through. If I set this down to 10 seconds per screen, it's going to be like really tight. And if you bring it to a very short range, it'll be showing you kind of in real time within 5 milliseconds, like this is what's happening to the knob right now. But when you kind of pull it into this range and have it trigger, you can add the trigger and it'll give you a nice stable idea of what's happening with your waveforms. So one of the things about this too is, how I'm multing out my gates here. I can add multiple cables to an output. You can't add multiple cables to an input. What you can do is you can add a mix and you can mix these signals, but you can't plug multiple outputs into an input. And that's kind of a holdover from the hardware because you don't want to shove, 5 different voltages into one control voltage port. It's potentially bad. It should all be operating on the same system, but it's not something, you don't really want to overvolt these things. Are there any questions on the Discord or anything?
When you say like you don't want to do X, Y, or Z, are you speaking from experience or like explosions or like burning up like hardware?
If you had like 3 different racks with different power supplies and you were running 3 different voltages into one port, they might be different enough that, you might get smoke and fire. But
so it's like a huge liability.
Yeah, I mean, it's just, and if you're adding voltages from these 3 things, your rack runs on plus and minus 12 volts. So the overall range is 24 volts. But most things kind of operate like control voltage goes 0 to 8 volts. Gates are usually 0 to 5 volts. And then audio kind of operates on the positive and negative because it is alternating current, because it's a waveform. But it's just generally good not to do an additive thing. See, when you're using this mix, in hardware, what's happening is each of these channels is running through an operational amplifier, just this chip that kind of regulates what's happening with all those voltages and adds them in the same range. But if you were to just basically plug a bunch of electrical outlets into the same spot, you're just going to risk like kind of overvolting it or overcurrenting it. Although everything's very low current in Eurorack because it's not, voltage is kind of the intensity that is pushing through the wire. Current is how much energy, or like, this is the electronics class, but so if you're driving a motor, you're using a lot of current, right? If you're moving mechanical things, you're using a lot of current. If you're playing with synthesizers, it really doesn't need much current, and they're not designed for much current. It's just, it doesn't even move a speaker because what you need is an amplified speaker at the end of it. So it's really just control and audio signals instead of something meant to drive a motor. So let's see. So as far as doing that kind of modulating other things at audio rate, I'm just going to go ahead and add another VCO here, and we can mess with that as an idea too. So I'll take that mix out of the filter here, and now we're just back to. I'm going to take a saw wave out of our second VCO, and we'll add that to the cut. And as I change the frequency on the VCO, you get all these crazy FM sounds. And we're using volts per octave for this, our main VCO right here, to kind of keep it within, reasonable notes. But since this one's just adding weird sounds, it doesn't really matter what we control it with. So I can take the sine wave from the LFO, and now we're controlling this frequency, which is influencing the frequency of the filter. And as I'm adjusting these knobs, like even though I have this oscillator being controlled by the low frequency oscillator, even though I'm using this to turn this knob, the knob's position is still the center point. So it's going plus and minus from there. So it's still being influenced as I do it. And the same with the filter. See, it's going, it's say turning within that range. So you can still mess with the knobs and still have them being remotely controlled by something that's doing modulation on them. Which is great when you're doing performance or doing something generative, so you can still be changing things, but they're still kind of acting on their own. So let's see, got myself a nice little stack of things going. I'm gonna try to simplify this up a little bit. So back to the basics here. We're still going, my keyboard is controlling the oscillator, and the sound from that is running into the filter, and we're taking the low pass out from that, running it into the VCA, which controls the volume, and then through the scope so we can see it, and then out to our sound card, our headphones or speakers or whatever. And then of course the envelope is controlling the VCA, giving it that waveform. Cool. So I'm going to keep this filter really simple. I'm going to give it a triangle wave now. Cool. So I'll give you an idea of like what happens when you have multiple oscillators. We can actually go back and we'll add a mix. So I'll pull that out of the filter for now. So I'm going to grab a triangle out of our first one, and a triangle out of our second one, and I can look at them and say they're the same frequency. So I'm going to take that mix between the two into our filter. And you see now we've got kind of these two interacting with each other. They're not necessarily hitting the peak of the triangle at the same time. And I can show you that in a different way. Instead of doing just the mix out, I'll just take the scope down here. I'll take these same two signals, controller command click, and take the inputs. So this is cool because there's two inputs on these scopes. That's an output. There we go. I'm going to bring the time scale up so we can actually see what's happening here. You can see even though these are the same frequency, they're hitting their peaks and valleys at different times. Try to get the time scale right so it makes a little more sense. There we go. So you can see they're just slightly off enough that if we were to look at one in static time, which is what's happening with that trigger, it's catching the one at the bottom of its cycle. And you can see that relative to that one, if you were to pause it, the other one is kind of swinging. So what we get is this more complex character. Now, if I were to take one of these, and here's another thing that you can do with VCV Rack is, you know, if you're clicking and dragging these knobs, you'll see that the frequency is going up. You could kind of move your mouse really slowly, but very quickly get out of range. I'm gonna double click this, bring it back to our middle C. And now because I've done that, it's actually caught into time. But what I'm gonna do is I'm gonna hold down Control or Command and then drag, and you can actually move it a lot slower. It's a more fine-tuned control. And so what I'm doing now is I'm playing, you know, we're 261 here, 262 hertz here, playing this slightly at a time. And as I move this, you'll see it has this beat to it. And that's because every time these cross at a negative point, so when you're hearing it kind of like mute in between, what's happening is imagine this being 1 and this being -1. So every time these are completely opposite, you're adding 1 and -1, and that is 0, right? So it's actually just canceling out, and that's called phase cancellation. Because the phase, you know, the phase is you're either plus or minus. So when you're +1 and -1, it just cancels out and mutes. So that's what's happening there. And that's called frequency beating, when you have two that are really close that are interacting with each other that way. But as I change this, you'll hear pretty quickly that this turns into a kind of frequency modulation. Now that's what's happening when this is being mixed, because this actually does the average of the voltages. So we have another VCA in the built-in modules, because this one can get a little annoying too, watching these things flash if you have a bunch of notes. But we have another VCA that acts as a mixer, like an audio mixer. So it doesn't sum the voltages in a literal way, it kind of mixes the change in the voltages like an audio mixer. Like if you had, you know, a band on stage and you've got drums running into it and guitar and bass and keyboards. So this VCA mix actually lets you mix in 4 signals, and if you don't use, let's see, I'll just take our waveforms out, well, I'll skip this mix. We'll run into channel 1 here, into channel 2 here. And then I'm going to steal that output, and there's a mix out here. Again, this is where it's nice to have the...
Just a little longer, please.
Yeah, exactly. We're back to the same problem where, you know, now the notes are just ringing out because we don't have any control.
Sounds like a warning drill.
Right? It's an Atari game, right? Especially if we switch to square waves, which is what the very old video game consoles are pretty much only square waves, because you've got, it's all, you know, pretty much digital circuitry in these old video game consoles. And digital circuitry is 1 and 0 binary, right? So you got on, off. Great for square waves. It's either on or off. You just do that really fast. So we can do the same thing here. I can take the gate. I'll take the gate for now. That way we don't have to split the, See, now you'll see, I've turned these down, so I'm just going to delete the old VCA. You'll see the control voltage going in, but now they don't. Cool. Now you remember what I did before was run these through a voltage mixer, and that gave us that cool frequency modulated sound. And now what I'm getting is just two very different pitches. I'm going to double click this, reset it. So now even though these are the same frequency, they're still doing this strange thing. And the other part of this is I'm only running volts per octave into the one, right? So I'm going to control command click, run the second one. So these seem to be synced up pretty well now. I wish I could get actually I could get a couple octaves lower. Oh. Now what happens if I'll control command click and I'll just go like slightly off, try to get that beating again. Now you see we get this sound that as those points are crossing. I'll pull the noise down a little bit too. I can add this a little more. Oop, that's too much. I think I went too far backwards. There we go. I think I hit undo and it just went ahead and undid like the past 20 steps. So that's cool. Remember to save frequently because sometimes things are buggy. VCV rack used to crash a lot, and now it doesn't so much, but running it at the same as Touch Designer, it will just die after an hour. Strange, but oh well. Cool, so I'm gonna add a little more difference in frequency here. Cool, now we got this faster phasing effect happening. Nice. But as you get too far out, you hear that it starts turning into a whole different frequency, and now you just got something that clashes. Until you maybe find a good spot for it. So, let's look at this. So we've got our middle C. So, I mean, keeping it close to the original is a good effect. So it's still near the same pitch, but just enough to mess with it, but not sound like a separate note. So once we go out of that, it sounds like a separate note. But what we could do, especially since modular synthesis by nature is kind of monophonic, you notice that we're only playing one note at a time. And VCV Rec actually has a polyphony feature now since version 2, and that's polyphony, so phone is in sound and poly is in many, so you can actually play multiple notes at once. It's a little more advanced, so we're kind of taking the sound design approach for now. Let's see. So we can kind of see what is, so this is like on a piano looking at, okay, there's 440, it's like A above middle C. You notice that where we keep our, where the default of the oscillator is 261.63 hertz, is that C right there. So let's say we want to add like a bass note an octave below, so it'll have the same, without getting into music theory, it'll have like the same tonal quality. This is actually going to be half the frequency. And this is a chart from the early internet, and that's like the highest resolution I can find of it. So that's good. But so yeah, we'll say 261.63, and if we want to add a perfect octave below it, it would be 130.81, right? So let's say we want to double that up. So 130.81, right? octave here, and then this one's kind of a bass below it. So now we have a mix of two frequencies that do play along with each other. If we wanted to do a fifth, like a lot of times with the monosynths, like with an MS-20, where am I? There we go. I do this with an MS-20 a lot, where I'll tune the two oscillators a fifth apart. That's called paraphonic, where you're still only playing one note at a time, but it's like you're going up and down a keyboard playing notes that are a fifth, because they're, I mean, you can set it to whatever interval you want, but a fifth is, you know, pretty pleasing sonically. So I'm going to go back to our piano here. Say, okay, so our middle C there is 261. So we're going to G. So this will be C. We'll say the relative is G. That'll be 392 hertz. So I'm going to take our second one, make it 392. And now when I play it, cool. It's like we almost have two notes without having to figure out the polyphony feature of this. Another fun thing that this has, especially if you're using the keyboard and being limited, I mean, also if you're looking at my Midi controller, I don't have a full grand piano worth of 88 keys, right? I do have octave switches on here, but since we're playing with this built-in keyboard, I'm going to right-click on our menu again, and we have an octave. And if I just go ahead and move our keyboard out voltage, volt per octave control, I'm just going to take this one out. And I'm going to click and drag here, controller command click and drag to the second one. Seems the same, but if I click here, cool. I think I'm not even going through the filter. So I'm going to put the filter after our mix. And I am going to get rid of that old mix there. We're going to take our mix out from our 4-channel VCA into the filter. Get a little drive on it now, a little resonance. Cool. So let's think about how we can kind of put this together in a way that we don't have to be hitting the keys all the time, right? Because this is part of the fun of modular, is we can make something that kind of plays itself. So I'm going to get rid of our scope here. We'll just keep everything else as it is. Now we don't necessarily have to get our pitch voltage or our gate from this keyboard. So I'm going to right click and I'm going to click Seek 3. This is our sequencer. So this has a few features going on already. And there's basically 8 steps times 3, so we have 3 different control voltages out. And it has a built-in tempo, which you can see the clock LED right here. Speed it up, slow it down. And then you can see each step click by here. They're little LEDs once you scroll out, but you can see we're on step 1, step 2, so you can see as it clicks through. So right now what we're going to do is I will just decide that we are done with our MIDI pitch control in. I'm going to take CV1 out and drop it into our octave control, and this will just be a good way to distribute to whatever we're, whatever we want to send pitch data to, we'll just do from octave for now. So now I'm still pressing a key here, but it's only triggering the gate. I can press any key and we're getting the same pitch, right? Because the gate is hitting the envelope, which is hitting our VCA here. Scroll out a little bit. So we're still getting the on-off data, right? We're just not getting the pitch from my keyboard. What we are getting the pitch from is the sequencer, but since these are all and I think pretty quickly you'll notice that doesn't necessarily sound like a scale, right? Or it doesn't necessarily sound musical. I mean, it depends. You're welcome to experiment with whatever scale you want, or not fit into any scale. But again, if you're playing with other musicians, you're going to get annoyed very, very quickly with your own ideas of what scales are. So I'm going to start resetting these, but we'll just kind of keep this idea here. So what we want to do is, because these are, imagine just putting out a voltage that just changes constantly. If you watch the tooltip here, right? You can go positive or negative, but it's just continuous voltage. There's nothing to tell it like, okay, stay within these clicks, because what you're doing is you're falling between the keys on a keyboard, right? Or you're falling between the frets on a guitar, which you can do with a fretless. But again, if you're not playing notes, the other musicians get annoyed pretty quickly. So how can we turn this constant voltage here into something that fits? So we'll just drop this from the Octave Control for right now. I'm going to right click, and we're going to add the QNT, which is a quantizer. And quantization takes continuous values and funnels them into a set value. So basically, as you're falling between these notes, right, our pitch is somewhere in the middle of this and this. A quantizer basically rounds things. It rounds numbers to the nearest. You know, if you're at almost an E, it rounds it to an E. And that way, I can take RCB out here, go into our quantizer input, and we'll just run through the octave again. And you can actually see it before I even let the notes play. It's already clicking it to notes. So, you know, we can... So we can do this manually, kind of get it into the scale that we want by quantizing to whatever note and kind of paying attention to which step it is that's kind of getting out of range. But what's cool about this is I could say, I don't want this note. I don't want these notes, that one. And it will just fall into a scale. So already, without knowing music theory, you can just kind of fake your way into it. And you can look up scales, like, easily. It's just online. You can say, okay, this set of notes is C major. You know, we'll just say, this is kind of C minor. I'm just, here we go. And that shifts like, never mind, I'm kind of jumping into this. So now we have control of where this is falling in a musical scale. And we've got our octave control. And the octave control also has an input, so if I wanted to have more fun with that, we could go back and add our low frequency oscillator. And this will probably get stupid really quick. Yep, really quick. So I think we're already seeing a problem here, is we're going out of range of this really quickly because our voltage might just be too much, right? Because it's the same as like having these are called attenuators, so that limits the range of voltage. It kind of turns down the volume on that range of voltage. Because as you can see, the volume is enough that it's pushing us right out of the audible range. So what we can do with that, since this doesn't have an attenuator, like the filter does, or like the oscillator does, I'm just going to go ahead and add an attenuator. So we have 8-vert here. This is 8 channels of attenuator / inverter. So an attenuverter. So inverting would be whenever positive voltage hits it, negative voltage comes out, right? And if you turn it all the way to the left, it'll just be the exact negative. If you turn it all the way to the right, it won't be attenuated at all. It'll just put out the positive. When you're center, it sends out nothing. So like, let's look at this on a scope. I'll bring our controller command click, bring this in. So we have 0 right now, right? It's right at center. Now if I start turning this up, turn up the frequency so it's easier to see too. There you go. So as I turn this up, we've got a little bit of volume here, right? And then when I turn this up, we're back to that same problem, right? So if we take this attenuated signal, I'll unplug that from the octave and give it the attenuated version. It's still hitting. Now as I turn down the volume on the amount of range that it has, we'll just pull down the frequency. So now we've got something more workable. We can get real bassy with it by just inverting it and sending it negative. And again, there's that offset. If we're looking at this, this is going between, say, 0 and 1. We hit that offset, it goes between, it goes through the 0 here, our center line. So that might give us a little more control over going up and down. And what's happening with this octave too is because, this is picking like octave 5, 4, 3, there's actually quantization happening in there too, because it doesn't have a continuous value between. It's always hitting one of those switches, basically. Cool. Is stuff making sense with that? Cool. I know we're just getting into the esoteric parts like quickly, but that's the fun of it, because you can definitely buy a Casio and play piano sounds, but I think the weirder we get here, the better, because otherwise, you could go way more conventional a lot more easily. Another thing is, I meant to mention this forever ago, but these oscillators don't necessarily need to be controlled by a volt per octave. So if I just add another oscillator here, VCO, I'm just going to run our envelope to it, because why not? We'll just put that on channel 3. Make sure I'm still triggering my envelope. Cool. And we'll just take a saw wave out to this channel 3 here. That's CV, not input. I'm kind of attenuating the decay here, but this is another spot where we're going to want to say, okay, this is too much range here, right? So we could use the 8-vert to attenuate it or invert it. But it also has this FM input for frequency modulation. So instead of trying to control it on a volt per octave scale, we can attenuate it this way. So you'll see, go back to our saw wave. It's going to be another constant. Actually, I'm just going to go ahead and put the envelope on here too. Cool. So we've got our envelope back. And because this is still dead center, we're not getting positive or negative, right? If you want lasers, rad. I love lasers. Make the attack faster. Right? Lots of fun. We can do the reverse, we can invert it. And just the same, we can actually make it, we can mix voltages here again. So I can say, we'll take a mix. We're going to take our, actually we don't even need a mix for this. I'm gonna show you. We've got our frequency modulation here, doing a little laser. And we can attenuate that. And then we can also have our volts per octave signal just going straight into here. Maybe. Just participate. Definitely killed that. Okay. We can run it from our octave, just the same as the sequencer. There we go. So we've still got this note control over it. Bring the sustain up. But every time I hit it, it adds that modulation of doing the little laser sound. So just to like keep in mind that you don't have to just send stable signals to things. You can do additive. You know, we can also add an LFO to it. Although that gets out of pitch really quickly. But it's doable. Yeah. So we're stepping through the sequencer here, and we're also modulating the pitch. And if I pull down the amount, right, because we have this attenuator built in, so the LFO is running into this attenuated input, so if I pull it up, it makes no sense at all. But if I make it really subtle, and run it into audio range, we've got these super complex things happening, and freezing signal. Who's left? Who's still going in there? Oh, self-resonating. There we go. This is where it's good to look at your inputs and outputs to see where the sound's coming from. See, I've got nothing in here. I do have a little bit of signal there, so I'm kind of seeing my filter self-resonate. Anyway. Let's see, I'll bring back from that tangent, we'll come back to I'm gonna get rid of that one. There we go. As you can see, we were going through that octave. So now it's kind of playing on like 5 octaves at once. And that's what's modulating, is it's just playing like 5 octaves worth of this keyboard all at once, which is ridiculous. Cool. Okay. Let's see, so we talked about that. How's everybody doing with stuff? Now the fun thing is we also have these two other rows that are in sync with these other steps, right? So, well, first I'll move the gates over. Let's make a mold for the gates. So what I'm going to do here, in hardware you have what are called mults, and it will just be like an array of jacks where you plug one in, you get 4 out. And those can be buffered where there's like active electronics that keep everything at the same voltage, because sometimes if you split voltage 4 ways, it'll dip a little bit. In the case of gates, I wouldn't really use that. I'd use a passive one where they're literally just all the jacks are soldered together, so they're all just connected. But if we want to do a thing where, you know, I've got this gate running to 3 different places, but I don't necessarily want to use the Midi anymore, so I'm just going to start moving these to an output here, just using the attenuator instead of a mult. And so now whatever, I'll just let that run straight through. Or I should say, because this is that a synthesizer or children crying? Right, yeah, I mean, it's kind of hard to tell the difference sometimes, so. Depending on how good you are at programming synths. Oh yeah, so the third function of this attenuator, as I just noticed by accident, when you have something plugged into this input, you can use it to attenuate or invert. If you don't, you can do what's called offsetting. So I'll just take this over to the scope, and we'll see as I turn this up, you're just manually changing the voltage. Get this other channel out of here, which I guess drops off on it. Anyway, so now that I've got this multed from here, this will help me so I don't have to move every time that I want to change the source of the gate or the source of the signal. I'll just leave all of these, you know, if I'm sending it to 8 places, I don't want to have to move 8 cables every time. I'm like, wait, no, let me do this. So I'm going to take the trigger out of our sequencer and let the sequencer clock it. And now that's going to all of our places. So I'm going to put the envelope back in our, because you'll see what this says for the output is trigger out. And triggers and gates are similar because what they're looking for is the rising edge here. Just gonna mute you for a second. What gates and triggers look for is the rising edge to turn on. It's basically a square wave. So you actually can use a square wave from your oscillator as a gate because it's all voltage. But what we're seeing here is the trigger is just this leading edge. It's very, very short. So if I run the trigger into, which I can run out from here, if I run that into our VCA, it's letting the sound through, but so quickly that you're not really hearing it, because it's just that. If we turn it up really fast, it'll get to the point where you can, maybe not. So what we want to do is just have that trigger gate going to our envelope. And then we'll plug the mix back in. There you go. So now the sequencer is controlling our timing and the pitch. Now we have these two rows left over. We got CV2 and CV3 out that step along with our note sequencer on the top row, right? So let's say we want to add some variety. So I'm going to take our CV2 and let's control the release of the notes. So you hear right now I've got some kind of longer notes going on. There we go. Get a little more volume out of it with the filter. So let's say we want to make that release shorter. Actually, sorry. Let's make it invert. Now here's the thing when you here's the thing to look out for when you're messing with control voltages is, like, let me pull this down to a negative, right? And then I'll pull this down to, now we're kind of double inverting, so negative times negative, positive, right? So if you want to actually have this knob be, you know, let's turn this down, then this needs to be up. Start pulling these down and get shorter notes out of them. May or may not work. So now we got some good variation going. Let's say we've got a whole nother row to play with, so I'm going to grab my CV3 and let's put that to the filter cutoff. We've already got that attenuator turned up a little bit. Turn it down, turn it up, do whatever. Still turn this cut off because we're relative to the input, so I can make the overall window of the up and down shift with it. And just for fun, I can mult out. I'll take our release one and also put it into the resonance. See what we get out of it. Sequencer also has a little run button right here, so we can just... Although since the release is really long right now, it will just hold on that note until it finally fades out. So let's see, what if we wanted to make it a little weirder. Also, you have a tempo control here, so this could be fun. We could let's take a triangle wave out of the LFO, add it to the tempo. Right, there's no limit to the amount of weirdness. That's cool. Another way we could do this, instead of having everything synced up like this, because every time it plays through, right, it's going to play the same pattern, even though it's varied between different qualities on each note. it's still going to play the same 8 steps. So, right click, and we're going to add a random module. And this is, as you'd imagine, unpredictable. So we've got stepped output, linear output, exponential, smooth. You can grab whatever you like. If we're doing modulation, I could just say smooth. So I'm going to put this into the scope, and we can kind of see what it's doing here over time. It's not quite a sine wave. It's just kind of picking random things to do. And you can change the rate of that. So like, let's say we wanted to, let's put it in an oscillator just to give it an audio feel as well as the visual feedback here. So cool. When you pull the shape down, it gets more steppy. When you pull it up, it gets smoother. So that's something. So let's slow down the rate. And instead of running that to the oscillator and being that weird, we could just run it to the cutoff of the filter instead. So I'm going to pull that experimental oscillator back out. And let's run our pattern again. Cool. Chaos. So you notice this is kind of stepping out of time with anything else. It's just kind of freewheeling. So we could get some controlled chaos in here. We could take the trigger output, controller command click, and add that in, and hit trigger. And then this rate acts as a multiplier of that. Maybe. Now this random module, not quite my favorite because it is a little unwieldy. I mean, it's good for some things, you know, just random modulation. What I like to do sometimes, and this will be probably the only third-party module I show, but that's fine. I'm going to take the audible one. This is one I have in my hardware rack. It's called Utilities on here. So this is a sample and hold. I'm just going to stop the sequencer for now. So what we've got here is a combination noise and sample and hold utility. So what sample and hold does is, say you've got a sine wave. Oh, I can show you. Instead of watching me wave my hands around, we can look at it. So we'll take, sorry, let me take an LFO. That'll be easier. Oh, and this is all searchable too, by the way. I can just say LFO. So let's take that sine wave, and I'm just going to plug it into our scope, and I'm also going to plug it into the input of our sample and hold. Now, if I take the output right now, put it into the second channel, we're getting nothing. If I take our clock signal from it, well, which isn't running, here. It's an easy way to do this. Like I said, you can use an LFO as a clock. You can use a square wave as a clock, rather. So if I were to do, so you can't drag multiple inputs. So let's look at the second input here. I'll say, okay, let's do that. We'll just make it a pulse, just like it's a trigger. Right? Okay. So we're going to use that as our trigger input for the sample and hold. I'll just pop this over here and hit the trigger. Now every time that pulses the sample and hold, I'll take the output and we'll see what it does. Every time the trigger hits, it snaps, it takes a snapshot of where that waveform is, and it holds that voltage. So it samples where the voltage is at that second and holds it. So pretty straightforward, kind of. So if we were to look at that, like let's say, I'm gonna drop this volt per octave, keep channel 2, actually don't do that. Let's go back to having our experimental VCO. Yeah. I'll take a triangle wave from here, go to channel 3. No, CP3. There we go. Okay. So if I were to take the original sine wave here and drop it into this. Right now we're just getting that. But if I replace it with a sample and held signal, so now instead of that consistent thing, we're getting sampled values at the rate that it's hitting the trigger. So that's kind of half of what we want to do with the sample and hold. The other half of it is, if I take this input out, I don't need this LFO. This has a noise built into it, right? If I don't have anything plugged into the input, technically you could do this if you wanted. That's fine. But it's what's called normaled, which means if there's nothing plugged in here, it defaults to this. So when you plug something in, it breaks the connection. So if I have nothing plugged into the input, what we're getting out, or what's going in, is noise. And every time that the trigger hits, the output is going to be quantized noise. So we're right back to random. And we can increase or decrease that rate as we want. So what I like to do is I can just take that output and we can go, you just skip the sequencer. I'll just run that random sound back into of course now our range is too wide again, so we'd want to attenuate. So this is like a lot of what's going on with this sort of synthesis is, there we go, take it back to normal. It's kind of taking something weird like a random value or anything like that and kind of massaging the values into a range that makes it make sense. So you're kind of sculpting chaos into some form of order. But similarly, I could just, add this to the cutoff. We'll have a sample and held cutoff, and then we can run this more structured thing. And since this LFO is controlling the trigger and not the sequencer, we're kind of getting these steps in between. I'm going to go right back to audio rate. Make a nice sun, so now we're kind of underwater. Cool. Does anybody have any questions about controlled chaos? I think what I want to do next is look at a conventional synthesizer and kind of work backwards, kind of reverse engineer. So one of the most popular synthesizers of all time is a Mini Moog. 70s classic, fat basses, very thick sounds, 3 oscillators. This is just going way off on the random sound. Awesome. Cool. So, I'm going to keep my MIDI, I'm going to keep my scope and audio output. I will even keep this mixer, maybe. Actually, let's delete everything in between. So if we're going to take a look at how the usual, this isn't a preset synth. Everything that's going on the panel is knob per function. So to change the sound of it, you actually have to physically turn the knobs. So this makes it a good candidate for us to like kind of take a look at and kind of see what's happening. So we saw the VCOs, right? So we've got our oscillator 1, 2, and 3. So we know we're going to want 3 VCOs. This has a little like rotary knob for waveforms, but I think we'll just plug in the waveforms that we want to use. We've got I can look down here too, stretching my neck. So then we've got volume for each oscillator, which I think we know is VCA, right? It also has a noise input, so we can add a little bit of noise to it, and that has its own volume that we can control through the VCA. So I'm seeing 3 oscillators and a noise source. So we've got that 4-channel VCA slash mixer, so we can just use that. Then we've got filter, so VCF. We saw cutoff. On the Moog, they call resonance emphasis. So it's just a matter of, terminology, and you'll see different things. On the MS-20, they call the envelope generator an MG, and I'm not sure why. You mess around with them enough, and you kind of get the idea of what's happening. So the amount of contour, right here, you see there's an attack, decay, sustain. They don't have release on them, but we can still use our same envelope. And the amount of contour is actually the envelope. It has its own filter envelope. So this is to control the cutoff. And then the loudness contour, of course, is our envelope that goes into the VCA. And that'll just be controlling all of the oscillators. And then volume, output, glide we could get into too, that'd be good. Cool. So let's say we want 3 oscillators. Sounds good. Already got our MIDI set up. So I'm going to right click, click VCO. Hit Control C and copy it, click out here, paste. Have to click outside each time, which isn't super efficient. That's fine. And I know we want a mixer for that. So let's take our 4-channel VCA mixer. And there's also a noise source here. So we have a noise module, a little skinny, there we go. And there's different, let me take my mix out. It has different qualities of noise. There's white noise, pink noise, red, everything. There's different definitions for these ones that I don't know, but white and pink are the most common. Thank you, that's loud. So that's what you'd hear out of a TV that's not on the channel, right? Pink is the wider frequency band. I think it's just, I think it's defined as like equal energy at all frequencies. So that's a thicker noise. These other ones, I don't know. I kind of feel like if you were to run your noise through VCF, you could get any of these. This feels like high pass filter. This feels like low pass filter, right? So whatever. What the Moog has is classic white noise. And I'm going to put that on channel 4. We want to have our... I'm going to start with all of these down because I'm smart. We'll put that on channel 4. We want our 3 oscillators to take up the first 3 channels. And So let's look at the waveforms we've got here. The Moog doesn't have pulse width modulation. Like here, it actually has 3 different clicks where you can get like a fat, a medium, and a thin square wave. But I think we can modernize it a little bit, right? So I'll just make square waves. I'll take the square wave out from all 3 channels. They all seem to be playing along. We could do something like give them each their own character. So that's nice. So we got our three oscillators and a noise source. Oops, keep them all straight there. Cool. Oh, and you could also set the color of these manually if you want to keep track of. Just new cable, that's a weird thing. Yeah. If you want to keep track of, if you want to set all the control voltages to one color and things like that. But it auto picks a color each time, and that works fine for me. So let's see. So we've got our 3 oscillators here. We're just choosing square waves for now. We can just drag them to the different ports later. That'll be fine. Each one of these has a different range. So what these range switches are is octaves. So that's part of what makes the Moog sound so thick. So I'm going to space these out a little bit here. And I'm going to grab our octave. Octave. There it is. And I'm going to do the same. Just copy and paste each place. So each one has their own octave control switch. And let's just go ahead and advance and just drag these octave outputs to their inputs. And I'm just going to drag our MIDI controller or keyboard into there. Now if I pull these up, should all be the same frequency. Now we've got this 3 octave deep sound. It's already looking pretty thick there. Cool. And noise. Cool. So, feeling pretty good with this section here. We've got our mixer, which is also the VCA. Has on-off switches, not a big deal. So there's our 3 volumes, our 4th volume for the noise. Then all of these, once they're mixed, go into the filter. So, now at our filter, they go into the VCA mixer, then they go into the filter, which seems to have moved itself from here to down here somewhere. Oh, there we go, that's the issue. VCF, there we go. All right, so we're gonna take our output from the mixer, run it back into the filter, take the low pass out. We get our add a little resonance. Nice. So I'm just going to cut off all the frequencies instead of bothering to turn all these volumes down every time. It's just has the same effect, right? So there's our cutoff, and what I'm seeing here is we've got a filter envelope and the amount that goes into the filter. So if we're looking at amount, we're going to be looking at the attenuation, right? So we don't need anything particular for that. But let's right click and add an ADSR here, our envelope, and we will make that the filter envelope. And let's see, let me grab my gate from there. Cool. let's turn this up. Nice. Don't even need a VCA, right? This is what I did with my modular synth. I bought an oscillator and a filter, and I didn't have enough money for a VCA, so I literally just turned the filter all the way down and used that as my volume control as well, just by controlling the envelope from a lab frequency generator from an electronics lab. Use whatever works, right? Cool. So we've got a filter envelope. We do actually want to use the VCA, so I'm going to add another envelope for that, and we'll kind of keep them lined up with each other for visual reference. And I'm just going to control or command click, and we'll just add that to all of these. Because remember, these are still the relative volume. And I'm going to control or command click and add the gate to that one as well. Pull this up. Say we just only want to have 2 oscillators in this patch. They actually feel a little offset with each other. So you hear how these are doing that phase relationship thing as well. They actually kind of sound like they're different notes, even though if you hover over them, they're the same note. So we'll say this is oscillator 1. Let's make this the source for the other 2. So I'm just going to control click this square wave out, because we want basically that same sharp rise that square wave has. We're going to add that to the sync of the other 2 oscillators. So there's soft sync, there's hard sync, and that's basically when it sees the that sharp uptick, it forces the second and third oscillator to restart their cycle at the same place, so that they're all in phase sync with each other. So if I were to pull this one in here too. See, it's kind of forcing it into the same place, even though it's different. It's kind of forcing it to sync there. And that way it stays in pitch, and then what you can do instead is use this to add more harmonic content. I know this is melodically like fantastic. But there you go. So we've got 3 oscillators. We can add a little noise source to it as well. So you bring it up all the way. It's a bit much, but it adds a little bit of character in the background. Just have a little bit of noise in there. Cool. So we've got our filter envelope. We have our VCA envelope. Volume is on the output. Output's all good. Let's see. Modulation mix. So it kind of, in this case, it's really, you can use like your oscillator 3 as an LFO, basically. But we've got free resources, so we can just add an LFO and we can route that wherever we like. So if we want to, oh, I don't know. You know, we could mix, CV mix. So we'll take the sine wave out from that, and we'll take the filter envelope. We'll mix those two together, and this one actually lets you attenuate both. I'm gonna say like just a little bit of that. Let's see what we get out of this. We can mess with it from there. So I want most of it to be the envelope. I like that envelope, but we can also give it a little bit of that afterwards. We'll actually just put this over here with that. Nice. Cool. We've got modulation options. My favorite thing that's missing from our patch so far is called Glide. It's also called portamento or slew limiting, depending on what synth you're talking about or if you're talking about electronics. So let's take a look. I'll make another scope, and we'll take a look at what's happening with pitch values. So when I play a pitch from the keyboard, right, each time I hit a note, it's just, especially if I pick a couple octaves different, it's just sending this instant change in voltage, right? Now what if you were to do something like you're playing a guitar and you slide between notes, right? So glide is sliding between notes, like you could do on a fretless instrument or anything else. So we can actually do that. So I'll put it before the octave. Actually, I'll put it after the octave is probably a better idea. Yeah. We're going to need, what did they call it in here? Oh, process. So yeah, that's where you're going to see that the term slew limiter, but you also see that your outputs here are slew and glide. So what slew is going to do is change, kind of just comes from the electronics world. It limits the rate of change. So if you were to take a square wave and say, actually that's the easiest way to do it, isn't it? I will take a square wave, put it into the input, and we're going to take the slew. And you can see what's happening here. It's like we've got this instant up and instant, that's pretty funny. It's like inching along. We've got this instant up and instant down, right? So what the slew does is forces it to slow down the rate of change. So as I pull this up, you see it can't go up as quickly, it can't go down as quickly until you get like a triangle or barely any change at all. So I like that. So in effect, what we can do, we can put our pitches in there. So we're going to take that, we'll take the output from the octave and run it into the input. Now slew always does that. It always limits the rate of change. So if I bring that down to our oscillator, we'll turn it up. Of course, the problem is now, if you hit notes, it's taking a long time to get to the right note, right? If you have a nice short one, then that's a little whoop, whoop, you know. But the longer the range between the notes, the longer that time is going to take to slide. So what I like to do is a little more controlled, is use the glide output. Yeah, we'll keep that in the middle there. So if I hit two notes separately, instant change. But if I hold down the first note and hit another one, it glides. So it's a controlled slide. If that's, oh, it needs a gate for that. I'm sorry. My bad. Okay, it needs the gate so that it knows when you're holding down one note and hitting another. So as long as that gate is engaged, it will slide between notes, and when it's not, it won't. So we'll add the gate to the gate input. Still separate. But when you hold a note, you keep the gate engaged, then it lets you slide. So not too bad. Cool. So that gives us pretty much everything that's on the mini Moog. The other thing I did forget here was these octaves. We went with the sync, which is one way to do it. If you flip the sync switches, OS3 control, it gives you that control over the harmonics. But if we wanted to keep individual control over these, I could kick the sync out. And you see that's awful. So I'm going to reset these to the same pitch. Now when I hit C, it works because they're all on C, right? But now they're missing, they don't have an input to the volts per octave, so. Right. So we're going to split our volts per octave out to the other octave controllers. That go to the other. So let's open up the filter a little bit. We'll turn down this modulation just to get a good feel for this. Now remember the trick with just slightly offsetting these so that they sound thicker? Just gonna hold down Control or Command and just drag slightly out. So at 261, let's just say 262. Put this one down a little bit. The idea is to like offset it just enough that it does these interesting phase relationships, but without creating the impression of another note or like being out of tune with itself. Then you get these fun like thicker sounds. I could even just like reset that one and bring it down. Now we have a thicker bass below it. Just have kind of a super thick 3 oscillator sound, a little bit of noise in it. Bring some of that modulation back in. And of course, all the same, we don't have to use the keyboard for that either. We can just go right back to quantizing a sequencer output. And I'm just gonna do that same Attenuate trick here and move that out of the way. Yeah, we'll take the output from the quantizer and then we'll get rid of these. Get rid of these guys. And we'll split out from here to all 3 of them. And make sure this is all the way up because it's volt per octave. And the same with the gates. I have a trigger. course, the more you do it, the faster you get at it, you know? Oh, these still need to move over. That's the gate. And when you hover, when you have a bunch of these things, it's nice to be able to see. It'll show you where all 6 of these cables are going. Super nice. But let's run this back through. Nice. I'm gonna run that input in and we'll just slew the output first. Now if we want to go back to, let's say, I want to have a 5th in here because this was a mono synth as well. Let's look at our values. 261, that's that middle C right there. Let's say I want to add the G, so 392. Let's make oscillator 2 392 hertz. So that'll be relative, like the same control voltage, the same volt per octave information is going out to all of them. But since it's relative to the knob position, it'll be playing a 5th off from the others. And of course, enough knowledge of how the synths work, you can kind of reverse engineer anything into this because there's not really much of a limit on what you can find. Like, I don't particularly like this built-in filter. I like the volt ones. I can swap this out for a. Oh, you can zoom this too. That's right. There we go. Let's see. What is that filter I like? Stable state variable filter. There we go. I'm just gonna swap this out. Take the input, take the output. We got low pass, high pass. We got band pass on this one. And then semblance, which actually lets you like slide between the 3 with this knob. So I'm gonna pick that one. If I move this to the left, we've got our low pass. I think this one just sounds so much better, but it's louder. But then as I move this to the center, we've got a band pass, which is, it's kind of high pass and low pass at the same time. It just has volume in the middle, and where that middle is moves based on your cutoff. So we'll just like straight up make that. It works better as well. So it's just kind of a moving window of what frequencies are coming through. So So then of course we can just modulate this all day with the LFOs. And these have attenuators on them as well. Subtle by making them take longer, slowing down the change. Don't like that filter. Keep those with that filter. What should I add? Shout something out. The what? You mean like here?
Yeah. Is that color dependent on the voltage?
Yeah. Yeah, I can actually show you with we'll just say offset. Offset. Oh, there it is. Yeah, I'll show you with this offset module and a scope. So we look at the output of this with the offset is basically just a voltage that you can turn up or down. So if we watch this output or input either side, to turn it up, the more voltage positive is green, and then 0 is nothing, and then negative is red. So yeah, when you're seeing the audio output here is just this kind of red and green flashing, that's just doing the same as that. And like when we're looking at the outputs of the outputs of like the envelope, it's going to be green just because it's a positive signal. Quick flash, just like the triggers. Yeah. Yeah, it's really handy to see. I mean, sometimes it kind of just fades into orange when it's doing audio rate stuff like that. But if you want to see, like, I know the LFO right now is not set to bipolar because it's just showing green. But if I switch it to bipolar, slow it down, maybe not that slow, but there you go. It's positive, negative. So it's really good for visual feedback altogether. I don't remember what that was plugged into. Oh well. Which I don't think it's anything right now. That's fine. If we wanted to play around with waveforms, you know, there's the switch on the Moog, these kind of rotary switches. What I think would be fun is we've got this thing called a sequential switch that's built in. Where it's there's 1 to 4 and 4 to 1, and what we want is 4 to 1. So I'm going to take all 4 waveforms and put them in the 4 inputs. Control Command click on that one to mult it out. And let's see. I'm just gonna where should I put it? I'll put it right here. So this will be a 1 oscillator patch, but we'll take the output, run it into the filter here. So what we're getting right now is just that sine wave, right? But this is basically, you've got 4 inputs. This isn't mixing into the output, it's a sequential switch. So each time the clock hits it, it will switch which input is going to the output. So let's add the trigger to that. And now for each note, it's stepping through the waveforms. So we can like do that with both. What's that? I'll do that with Oscillator 2 as well. And I'll just swap out the order, I'll reverse them. That's fun. Control there. Instead of putting that in the filter, I'll just drop it back into the VCA. So this would be Oscillator 1. And there's our 1 there. I'll take out 2, and then I'll make this our 2. Gotta add the clock to that second one. We'll mult out the trigger again. And, oh, you're right, mix, back into the input. There we go. Nice. Now we got these going in reverse order. So you won't have two of the same waveform. We'll always just have a bunch of different waveforms bouncing off of each other every day. They do what?
Can you remove it?
Oh yeah, you could actually take out. Yeah, you can take out triggers as you like. Which in this case, because we have that slew, it's gonna give it time to. And since we also have these individual trigger outputs, we can kind of spice this up a little bit. Let's add some sounds in here. We've already got a noise. Why don't I take a look at? I think blue is kind of a nice thin sound, right? Let me add another. I'm gonna add another VCA mix, and we're just gonna plug. Let's see. Where do we want to go? Let's say, I'm going to use this one as more of a mixer for the first channel because we're just going to chain. So we only have 4 channel mixers right here, right? So I'm going to chain. We'll just leave that turned up and we'll run that mix out. Maybe. Oh, CV1. Always forgetting that. There we go. All right. We'll scoot this over. So here's where we can get really out of hand. I'm just going to copy this noise module, put another one down here. And we will add just a 1-channel VCA. And I'll start with white noise and see how it goes. And I'll put an envelope there for ADSR, an envelope out, the VCA in. I know I want this to be, I'm making a snare drum here, by the way. Or maybe a hi-hat, we'll see how it sounds. So I'm gonna make it just a quick attack. And we will take the output and we're just gonna run it into the mixer over here. You can scroll while you're holding the mouse button to drag things out. Nice. Okay. Let's see. I think there's a manual trigger built in. Guess not. There are modules which is like. Yeah. The trigger. Let's see. I know there's Logic will do it, but
in the current row, is that pulses with a push trigger and gate does
Which one are you looking at?
Middle row, second from the left.
Pulses?
Yeah.
Yeah, there you go. That's it. Yeah, there's a third-party one that just looks like giant arcade buttons, which is nice because it makes me kind of want a touch screen because it could just be like that. It probably wouldn't work very well, but yeah. Let me use pulses. So we'll just take the gate output, put that into the gate input, and there we go. So every time I hit that, oh, right. Cool. Let's see about some different types of noise. Violet. Still probably want a little bit of filter on this just for character. Filter before the VCA. Up that in. I guess I'll take a low pass filter. Maybe a high pass. Alright, so we can get rid of pulses now. Just need an idea of that. Now we could take one of these individual gates out. Of course, that's just one. So we want, let's just mix these. Let's take the 3 and the 7, kind of the offbeat. You know, I think that other filter with the bandpass might be better in this case too, so get rid of that one. Let's give it a nice bandpass. That was, what, violet noise? Sure. Input, take the band pass from this to the input of the VCA. Get rid of that. Cool. I like that. So yeah, it's not just synthesizer sounds. You can make drum sounds, you can make lasers, you can do whatever. And let's say we wanted to have a bass drum too. We could just put that on the 1 and 5. So I'll copy the mix. Oops, not paste. Copy the mix. And I'm going to take the 1 and 5 here. And then let's copy an envelope. And I'm going to take the wavetable VCO. This is similar to the other one, but it actually morphs between the different waveforms. So I got a nice shape like that. I want to make a bass drum, so I kind of want to keep it smooth, but maybe a little bit rough to give it some flavor. Especially since we don't have big subwoofers in here, so it doesn't have to be like clean, it just has to be audible. So we'll take our envelope to the VCA, we will take our wavetable out to the VCA, bring this up to our final mixer. And I'm gonna bring our mix to the go ahead and mute that channel 1 and see if I can get a good. A little bit of decay. Now another thing we could do is when you have a kick drum sound, a lot of what you have is you've got the initial hit of the beater against the head of the drum, and then you've got the ringing out. So when you have the kick drum, that's like the biggest drum, because the more space, the bigger the head is, and the more space it has to reverberate, like the lower the frequency, right? So we've got our low frequency, but we want to emulate that hit initially. So that initial hit could be our envelope. So I'm going to mult this out to the frequency. Not great, but you know, it's something. Might add in a filter here too. Put that before the VCA, low pass, because we've got a nice kick drum. I'm going to go ahead and mult out to the filter as well. You get the idea. Making kick drums be a little bit difficult without a subwoofer. So, I mean, you might even want to just add in a noise, you know, add some white noise with a very, very quick attack and decay. So it's just an initial hit. But what we could also do, since we have these volt modules, there's actually a kick drum synthesizer, Trummer 2. So I'm just going to grab that instead. Take a gate here. And we'll take that output that was going from our kick drum. There we go. And then we can do things like move these notes around. Kind of make beats manually that way. Not like the most efficient way to do it by any means. But you know, that's all right. We can also add a likelihood. Try to get this a little louder. Say we wanted to have hi-hats. I'm just gonna double this up. We'll add some noise here. I'm gonna grab the trigger because that's on every beat. And we'll say we wanted this to be our hi-hat. Right now it's a kick drum, but has a noise channel too, so I'm just gonna pull that. I'll mute the snare drum. course, this is the point at which it gets really easy to just like overload with cables and let's see if I can get this to here. There we go. Cool. So right now we've got this going on every beat, but if we wanted to have like a degree of randomness to say our hi-hat in here, it's pretty loud. There it is, built in. Logic is also a random. Oh yeah, we can go back to the random module. Now let's put our gate into the trigger here. And then we can take the trigger out over here. Now see, we've got trigger probability 100%. If I pull this down, it only hits on some. You can make this more likely, or like fairly likely to ever happen. That's one way to do it. Another one is in audible instruments. There's what's called a Bernoulli gate. This is another probability module. So we'll go into here, and our output A. So when this is up center, when this knob is up center, basically this is a coin flip module. It's basically 50% probability that output A will be triggered or output B will be triggered. If we move it over here, it's like every one. So this will do the same thing with some random, but leaning towards A to be leaning towards B. So if we wanted to have like two different noise samples, we can take that gate. Where's my noise? There's my noise. All right. We can just make that other kind of snare sound. Kind of clicking back and forth between the two of them. I think I timed my coffee great. Boom, out of coffee. Awesome. This is something I haven't messed with, but the Quantizer has an offset. Which I guess if you could get it to be even, I don't know how it would. So you should be able to shift keys, but you might have to do it precisely. You might just have to tell it like 5 semitones. And then you can just get into like way more interesting oscillators than the bass one here. Where'd I put it? There we go. It's a macro oscillator. It's basically like our wavetable down here. but that's what it is. I'll just grab the first out. Volt per octave. And what channel did I open for myself here? Channel 4. Let's take the output from this. It says way more waveforms. And they each have these kind of... What's that? So obviously you can just sink so much time into this. So a plucked one, which I'm used to the hardware ones, I can't remember the names of all these. Oscillator, texture, resonator, there you go. This one's fun because it takes gate inputs, so it kind of has a built-in VCA with it. Grab my gate from the sequencer. Control click out. And strum input. So their hardware module has these two buttons that switch between a bunch of modes. This is kind of nice, it lets you cheat. You can just right click and you can click these different. The problem with some of these is you don't have the same scales. They just use an arbitrary scale instead of hertz, so you have to tune it yourself. So, yeah. Obviously, you just keep going on like that. Oops. That's not the output. Cool. Any questions? Cool. You feel like you learned something? A little bit? Awesome. And that is just a little bit of VCB rack. There is a ton of material online, a bunch of great YouTubes. I would look at the dates on some of them because VCB rack shifted significantly in function from version 2. But like anything the past couple of years, especially Omri Cohen does a lot of like cool videos, and Red Meat's recording. They both do a lot of cool videos with VCB rack, kind of dig deep into the features and a bunch of the third-party plugins. So cool. Well, thanks for coming. It's been fun. I basically got to jam all morning.